Okay, let me start. In this Monday, we were talking about the Elliott factorization, right? So let's recap. So first of all, the matrix multiplication such that the P times C is equal to A is the kinds of synthesis, right? So those kinds of operation fuse the information from the matrix P and matrix C. So this is called the synthesis procedure. In reverse way, if we decompose the matrix A into the matrix P times matrix C, this procedure is called the factorization or matrix factorization. So by using the matrix factorization, we can analyze the property of the matrix A by using the two sub matrix P and matrix C. Okay, so this is concept of the factorization, and specifically we were talking about the Elliott factorization method, right? So what is the Elliott factorization? If A is equal to L times U, when L is the m by n lower triangular with n's on the diagonals like this, right? And U is the m by n echelon form of the matrix A, something like the right hand side. So in this case, this decomposition method is called the Elliott factorization, right? So why they are so useful? Okay, let's think about the problem of the ax equals b. So we want to find the solution of solution of x that satisfies this equation, right? So the straightforward method to solve this problem is the x is equal to the inverse a times vector b, right? So comparing to this procedure, by using the Elliott decomposition, we can efficiently solve the this AX equals B problem, right? So okay, if there is the LU decomposed a matrix such that L is the this kind of the form and the U is the this kind of form, then we can represent the ax equals b something like this one, right? Then if we define the y is equal to ux, then we can decompose this problem as a two sub problem, right? Ly equals b and ux is equal to y, right? So first of all, we can solve the ly equals b for vector y, right? Then we can solve the ux is equal to y for x. So finally, we can get our result, our solution x, right? So comparing to this one, this procedure can have the more efficient computation time. So for example, if you see this note, you can understand why the Elliott decomposition based method much efficient and more efficient than the original A inverse times B method, B procedure. Okay, so the example we talk about how can we solve the A equals B problem by using the Elliott decomposition, right? So first of all, by using the matrix L and vector B, we found the vector Y, right? Then by using the vector Y and the matrix U, we finally found the matrix X, right? Vector X, which is the solution of the Ax equals B, right? So when you see this page comparing to the straightforward solution, A inverse times B, then our Elliott decomposition based method have the smaller arithmetic operation, so it is more efficient. Okay, today we are going to talk about how to decompose the matrix A into the L matrix and U matrix, right? So before that, let's recap the elementary matrix. Okay, do you remember what is the elementary matrix? What was that? What was the elementary matrix? Elementary matrix is the matrix that is obtained by performing a single elementary row operation on the identity matrix, right? So what was the elementary row operation? There was the three kinds of the elementary row operation, right? So first one is the replacement, the second one is the interchange, and third one is the scaling, right? So let's assume that, let's say the Ri is the arbitrary row in the in matrix matrix A. Okay, let's say there is a matrix A, right? So yeah, let's see. So what is the replacement? So let's say the Ri is the ith row, then Rj is the jth row. Then this means that the original Ri can be replaced by the Ri plus the constant k times Rj. So this is a replacement rule, right? So we frequently use this procedure to row reduce the original matrix A, right? So there is another rule is the interchange, right? So this means the Ri and Rj rows changed, right? The final one is scaling. This means that the previous row is multiplied by the constant some constant k as a new row, right? So for example, okay, before seeing the example, I want to show the generalized form of the matrix multiplication. So the general form of the elementary matrix form is as below. So let's say the size of the matrix A is the size of the matrix is the m by n, right? So first of all, in this case, what is the size of the elementary matrix? What is the size of the elementary matrix? M by n, right? Why? Because this elementary matrix is multiplied on the left-hand side of the matrix A, original matrix A, right? So in this case, the size of matrix A is m by n, so the elementary matrix size should be m by n, right? Because these two values should be same, right? So first of all, in the replacement rule, the general form of the elementary matrix looks like this. So okay, this is the row 1. Let's say let's say row I. Row row I. Then by using the this matrix, we can perform the replacement. It means that, okay, let's say this is the Rj, right? So and then this matrix have the same number of the row and same number of column. So it means that this is also J and this is also I. So it means that in Ri, if we put this k value, then we can perform the replacement, right? And what about the interchange? Okay, let's say this is the Ri and Rj, right? If we move this one into here, one to here, then we can interchange each row. Okay, then what about the scaling? If this is the Ri, then by just put the number k in here, yeah, we can perform the scaling. Okay, so this is the elementary matrix, right? So let's see the example. Let's say there is a matrix A, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, then first of all, let's say elementary matrix E is going to be 1, 1, 1, 3, like that. Then like this one, like the replacement row, right? Then what is the E times A? What is that? We already know how can we multiply the matrix, right? Then what is that? 1, 2, 3, 4, 5, 6, right? Then 3 times 1 plus 7, 3 times 2 plus 8, 3 times 3 plus 9. Why? Because this one is this row times this column, right? This values is this row times this column. This one is this one and this one, right? So when you see the last row, it means that R3 is replaced by the original R3 plus 3 times R1, right? So as you can see here in the replacement row, this E times A is exactly same procedure of the replacement row, right? So this is the elementary matrix for replacement. Then what about inverse of elementary matrix? Inverse of this elementary matrix. Actually, we didn't talk about the matrix inverse yet. I mean, we didn't talk about how to derive the inverse of the matrix A, but there is a rule. The inverse of this elementary matrix is the -3. Why? Actually, to derive to prove this concept, we need some kind of the definition. But we can easily see that E1 times inverse E is going to be 1, 3, 1, 1, -3. So it means that 1, 1, 1, 0, right? Why? Because this term is defined by this one. So 3 minus 3 equals 0. So we can show that E times E inverse is identity matrix. Then we can easily derive the E inverse times E is equal to I. So we can, in this definition, we can see that inverse of elementary matrix with this term is just negative values of the original elementary matrix, like this. Okay, so this is the general rule. So it looks like this. So inverse of the element replacement to matrix is just replaced by the -k, something like this. Okay, and interchange law, the inverse of interchange law is just the elementary matrix itself. And the elementary matrix of the scaling, inverse of the elementary matrix of the scaling is just replaced by the 1 over k, right? So you can easily derive these two kinds of term by yourself, okay? Like this one, okay? It's very easy. So please remember this property. So we will use this kind of concept in the algebraic decomposition, okay? So what is the property of the replacement operation? Okay, let's say the matrix A is the elementary matrix 1, 2, 3. So they are all elementary replacement matrix. So let's say the first elementary matrix is the let's say 2, okay, and let's 3, 4. What is that? Then what is that? To derive this matrix multiplication, we compute something like this, right? Something like this, and something like this. You know how to do that, right? Then, if you derive this multiplication, you will get the 2, 3, 4. Okay. Please check this is correct or not. I strongly suggest you derive this one yourself, because this property is really important in the relative decomposition. But anyway, the multiplication of the elementary matrix of the replacement rule is really intuitive, right? Then what about the inverse of the matrix A? So what was the inverse of the elementary 3? Elementary 3 is something like that, right? So answer is 1, 1, 1, negative 4, right? And 1, 1, negative 3, right? 1, 1, negative 2. So from this will be the from 1, 1, negative 2, negative 3, negative 4, something like that. So comparing to this one, the inverse of the multiplication of the elementary matrix is just a minus negative sign on the constant value. So this is the rules or the property of the elementary replacement matrix. So please remember this one. So we will use this kind of operation, okay, from now on. Okay, so okay, here's the assumption. Let's suppose that matrix A is the n by n matrix that can be row reduced to an echelon form, right? So echelon form without row interchange. We will generalize this one, but here we just assume that there is no row interchange, and we can just use the row replacement rule to derive the echelon form of the matrix A. So the original matrix A is row reduced to the echelon form U using the only row replacement that add multiple of the one row to another row. Okay, so like this one. Okay, so okay, by using the lower triangular elementary matrix, what is the lower triangular elementary matrix? Just like this. because they are whole lower triangular shape, right? So to low reduce the original matrix A into the matrix U, there are E1 through the EP elementary matrix, right? So we can derive this whole procedure something like this, right? Then in this case, we can represent the matrix A as a inverse of the multiplication of the elementary matrix with the echelon form of the matrix U. Okay, then L times U. I mean, L is going to be inverse of the E1 times E2 times through the EP. Okay, so we can conclude that the matrix L can be represented like something like this. Okay, so here's the key observation. The product, the E1 times E2 times through the EP of a lower triangular elementary matrix, right, is also a triangular matrix, right? You already know from here, right? They are all lower triangular matrix, right? And this inverse of this product like D is also lower triangular, right? Something like this, right? Okay, so here is the observation, right? So let's say before starting, let's say this is equation 3 and this is equation 4, let's say. Okay, so the low operation in 3, like this one, okay, which reduce the matrix A to the matrix U, also reduce the matrix L into the identity matrix. Something like this. Why? Because if we apply the same law operation to the matrix L, and matrix L was the inverse of this one, so this will be the identity matrix. So it means that same law operations on matrix L will generate the identity matrix. Okay, so this is the observation to construct matrix L. Okay, here's the algorithm. So here's the algorithm for the LU factorization. First of all, low reduce the matrix A to an echelon form U by sequence of the row replacement operation, if possible. If not possible to derive the echelon form U, the original matrix A cannot be decomposed into the matrix L and matrix U. Okay, so if possible, please low reduce the original matrix A to the echelon form U. Okay, and then place the entry in L such that the same sequence of the row operation reduce the L to I. What does it mean? Actually, there are very fancy systemical way to derive the LU factorization. Okay, so but people starting the systemical way, I just want to show you the very high level intuition why the systemical way works well. Okay, so first of all, before starting, here is some description, step 1 and step 2. Step step 1 is not always possible, right? So when it is, the argument above shows that the LU factorization exists. If there is no elementary row operation that can generate the echelon form matrix U, then there is no LU factorization. Okay? Then by construction, L will satisfy this, right? From this observation, right? It's very intuitive. Then L will be the invertible, right? If you remember the invertible matrix theorem in the what's that? In the last week's lecture, then if the matrix form looks like this, then the matrix L is invertible, and the inverse of the matrix L is this one, like this one. Okay. So we can say that inverse L times A is equal to U, so A is equal to LU. Okay. So this is very intuitive explanation of the step 1. And step 2 will step 2 procedure will produce the acceptable L. Then we will see how can we estimate the matrix L from the original matrix A. Okay. Before that, let's see the intuition first. Okay. Let's see the example. Find the LU factorization of the matrix A, something like this. Okay. Matrix A is something like this. So, okay. First of all, what is the size of the matrix A? 4 by 5, right? Then what is the size of the matrix L and matrix U? What is that? What is that? 4 by 4 and 4 by 5. Do you know why? Why? Because the A is the L times U, right? So the size should be something like that. Okay. So first of all, we have to low reduce this matrix A to the echelon form. Okay. So then how can you do that? How can you do that? First of all, we have to remove this one by using this rule, right? Then what kind of rule replacement rule should be used? R2 will be the R2 plus 2 times R1. R3 will be the R3 negative 1 times R1. Okay. R4 should be R4 plus 3 times R1, right? Right. Then what is the matrix E1, E2, and E3 in this case? What is the matrix E1 and E2 and E3 in this case? Okay. Okay, let's write here. What is the E1? 1, 1, 1, 1. If E1 perform this one, right? Then it will be what? 2 here, right? What about E2? E2 like this, so E2 like this, right? Because of this negative 1, right? Then what is the E3? E3 looks like this. Okay, so something like that. Then what is the E1 E3 times E2 times E1? What is that? What is that? 2 minus 1 3, right? If you remember this one, it should be something like that, right? And then, okay, we make a 0 here, and then we have to remove this part by using this rule. Okay, how? By using the another elementary matrix E4 and E5. Then, so how can I remove this one and this one by using this one? The E4, the shape of E4 should be looks like this. Why? Because the 3 and minus negative 9 will be the minus 9 will be removed by the 3 times by adding the 3 times 3, right? 3 times 3. So this is the 3. Then what about E5? What about E5? What about E5? What is that? Something like negative. Negative 4. Okay. So the E5 times E4 will be 1, 1, 1, 1, 3, negative 4. Okay. Okay. So then what next? What next? One next. There's already zeros here, right? So we have to remove this part by using this one. Then, okay, let's say this is the elementary matrix 6. Then, what is that? What is the elementary matrix 6 here? From this one and this one, we can say that the elementary matrix C should elementary matrix 6 should be something like that, right? Right. Okay. Okay. Then finally we get the echelon form of the matrix A. So this is the matrix U. Okay. Okay. So let's think about the matrix L. Okay. So E6 to the E1 times matrix A is the matrix U. Like this, right? Then what is the matrix L? If we multiply the inverse of this one, right? Matrix A is going to be this inverse times U, and then A will be the L times U. Okay. Then what is L? Here, what is L? If we already E1, E2, E3, E4, E5, E6 from here, right? Then, first of all, let's think about this one, okay? What is the E6 through the E1? If you remember this rule, we already know that by just copy and paste the value to -3 here. So 2, -1, 3, and from here 3, -4, right? 3, -4, and -2, right? With the inverse, right? Then Then what is the inverse of this matrix? What is the inverse of this matrix? -2, 1, -4, -3, 4, 2, right, something like that. Okay, so from the relationship between this one, this one, this one, this one, this one, with the this one, this one, this one, this one, this one, this one, we can easily find the matrix L like this. So finally, this is a matrix L. Okay, so this is the procedure to estimate the matrix L. Okay, so actually, this kind of the procedure is also very intuitive, right? So we can understand what's the meaning of this each term during the low reduction algorithm, right? Fortunately, we have a very special systemical way to find the matrix L. Okay, so I will let you know how can we do that. Okay, so okay, first of all, we have a matrix A, something like that. Then we will low reduce this matrix A to the echelon form of the matrix A, denoted by matrix U. Okay, so the first way is to highlight the entry in each matrix that are used to determine the sequence of the row operation that transform A onto U. So what does it mean? Okay, let's just highlight the entry that are used to determine the sequence of row operation. So in the first procedure, we have to use this one, right? To make a 0 here, right? And what next? We have to use this one, right? Then what next? This one. Okay? Then finally, actually it's done. But this 5 is also can be used to low reduce. But actually it's not important. But let's just highlight this value. This value also. Okay. So and then this one. From here, right? The highlighted entry determine the low reduction of the A and B. From A to B. Okay, so at each pivot column, divide the highlighted entry by the pivot and place the result onto M. So in this case, let's divide this column by 2 by using this pivot value. Okay, so the result is the 1, -2, 1, -3, right? What about this? Divide by 3 here, right? So this will be the 3, -3, 4, like that. So in this case, -2, right? So it will be the 1, 2. Finally, then divide by 5, so it will be 1, like that, right? So finally, the matrix L is something like that. Okay. Actually, this is very intuitive and very easy to find the matrix L, rather than using this kind of the procedure, right? So this is very efficient systemical way to find the LU factorization. Okay, but before using this kind of algorithm, please exactly remember and understand why we can get the matrix L from the row reduction algorithm. Okay, so this is because of the property of the elementary matrix. Okay, so please remember this old kind of procedure to factorize the matrix A into the LU matrices. Okay, so finally, in practical work, the row interchange are nearly always needed. Okay, so if you remember the pivot position, partial pivoting, the partial pivoting is frequently used for the high accuracy, right? What was the pivot position? Partial pivoting. What was that? What was that? Okay, let's see here. The partial pivoting was that if there is the value something like this on the column, if we select the highest absolute values on this column, then the machine or the computer can efficiently find the solution than this original matrix form. So this was the partial pivoting method. Actually, as a human like us, we don't need to the partial pivoting. Actually, it will help, but it's not an important issue. But for the machine, it is really important because the efficient. When we think about the matrix like the 100 by 100 or the 1000 by 1000, we have to consider the computational time to derive some kind of algorithm. But so the partial pivoting is the most one of the most important issues, right? So in this case, we cannot use this kind of algorithm, right? Because we assume that there is no row interchange, right? Then how can we generalize this LU factorization algorithm? So here is a new algorithm, the permutative LU factorization. Actually, this is also very intuitive. What is the meaning of the permutative or the permuted? It's just like that. The permuted means something like the interchange between the row. Okay. Then what we want to do is we want to find the permutation matrix P first, and then permute the original matrix A by the P times A as a new matrix A, something like that. And then we can apply the same LU factorization algorithm, right? How? Okay, let's say we want to find the solution X times B. Then if we multiply matrix P on left hand, right hand side individually, then we can get this equation, right? So from here, we already know the PA is equal to L times U, right? So by writing Y for UX here, we can first find the solution of the vector Y from this equation. Then we can solve the matrix U from this equation. Okay? So main difference, sorry for that. Okay, so comparing to the original where is that? Sorry about that. Yeah, here, comparing to this one, by using the permutation matrix P, we can solve the Ax is equals B into the two-sub problem, something like that. So then what is the permutation matrix P? The permutation matrix P looks like this one, interchange matrix. Okay, so by using the interchange matrix, we can derive the permuted Elliott decomposition algorithm. Okay, so this is the end of the Elliott factorization method. So actually, to efficiently solve the Elliott factorization problem, you need some practice to solve this. So we will have some homework to solve some kinds of Elliott factorization problem. So I really believe that you will be familiar with the Elliott factorization soon. Okay.